All right, let's dive right into this explainer. Today, we're looking at a really fascinating way to just absolutely elegantly refactor code. We're going to replace some incredibly tedious boilerplate with pure mathematical logic. We're exploring a brilliant piece of Haskell programming that perfectly shows how, just getting a deeper understanding of underlying data structures can completely transform the way we write software. We're going to take a super messy, brute force approach to character mapping and turn it into something incredibly slick.
So, here's the question for you. How do you turn 90 lines of tedious, hard-coded mapping into a single, elegant line of logic? I mean, this isn't just about saving screen space, right? It's about reducing that cognitive load on anyone reading your codebase. It's about preventing future errors. And honestly, it just feels immensely satisfying to pull off. And that is the exact programming challenge we are going to solve right now.
Section 1, the boilerplate burden. So the original author ran into this highly specific problem when converting Chinese numerals in chapter numbers into digits. To do this, you basically have to map standard characters to their full-width equivalents. Now, initially, the developer just mapped every single character manually. So a standard X maps to a full-width X, standard Y to a full-width Y, and so on. Now, sure, initially, this is incredibly explicit, you know exactly what is happening. But apply this to the entire alphabet and all the common symbols. Yeah, you end up with 90 lines of manual character mapping. It becomes incredibly noisy and just an absolute nightmare to maintain. It is the classic boilerplate trap.
Chapter 2, the magic offset.
Whenever you see sequential data being mapped manually like that, your developer instinct should immediately start tingling. There is almost always a hidden mathematical relationship just waiting to be discovered. And the crucial point here is this specific hex code, 0xFE00. Now, this isn't just some random string of numbers and letters, it actually acts as a magic key. The creators of the Unicode standard, they didn't just throw full-width characters wherever they felt like it. No, they placed them at a very specific, consistent distance from their standard ASCII counterparts.
So check this out. If you take the underlying integer value of literally any standard ASCII character, let's just say a lowercase a or an x, and you simply add that magic offset of 0xFEE0, the result is the exact correct full-width character you need. It is a perfect one-to-one mathematical translation, absolutely no hard-coded lookups required.
Now, to actually implement this math in Haskell, we leverage a beautiful feature called a list comprehension. For those who might be a little newer to Haskell, this is simply a syntactic construct that lets us create a new list by dynamically looping through existing lists or ranges. In our specific case, this is going to serve as the engine to loop through the entire standard ASCII range, from the space character all the way to the tilde, evaluating our math along the way.
And here's the payoff. This single elegant line of code successfully replaces those 90 lines of hard-coded mapping tables. We're just taking the character C, drawn from our ASCII range of space to tilde, we convert it to its numeric enum value, add our magic offset 0xFEE0, and then just convert it right back to a character. Boom! A perfectly generated mapping list executed instantly at runtime. It's clean, it's logical, and it entirely removes the boilerplate burden.
Moving on to Section 3, the encoding trap.
But wait, even elegant mathematical code can run into some real-world dangers when it's actually deployed. For characters outside of that sequential ASCII range we just talked about, like specific typographical quote marks, you do still need to map them manually. Now, using literal Unicode characters directly in your source code feels completely natural, right? And it reads perfectly on your screen. You just type a left quote and you tell it to map to a full-width bracket. But this actually creates a very subtle vulnerability.
And that vulnerability stems from environments. Basically, if another developer opens your code in an editor that defaults to Latin 1 encoding instead of UTF-8, or if your CI/CD pipeline has a slight misconfiguration, and let's be honest, it is always a CI/CD misconfiguration, those literal Unicode strings get totally scrambled. The compiler doesn't necessarily know it's wrong, it just obediently reads the corrupted byte sequence. And that leads to silent, incredibly subtle bugs in production where your text formatting just quietly breaks for the end user.
Which brings us to Chapter 4, Bulletproofing with Hex Escapes.
We really need to defend our code against these unpredictable environmental failures. So by replacing the actual literal characters with their hex escape codes like \x201c for the standard quote, you completely bypass the risk of incorrect editor encodings. These are just standard ASCII representations of Unicode points, meaning they will absolutely survive any text editor, any Git transfer, and any pipeline completely intact.
And here is our final bulletproof structure. We safely map the few specific, non-sequential quotes using those rock-solid hex escapes. Then, using Haskell's concatenation operator, the double plus, we attach it right onto our magical list comprehension that handles the rest of the alphabet mathematically. It is readable, it is highly condensed, and most importantly, it is environmentally robust.
Which brings me to this final thought. If a simple math offset and a quick check of the Unicode standard can replace 90 lines of brittle code, what hidden patterns are waiting to be refactored in your code base today? Seriously, take a close look at your massive switch statements and those giant dictionaries. The math is out there, just waiting to make your code bulletproof. Thanks for joining me for this explainer, and hey, happy refactoring!